let's try that. Uno mas. So again, no, I'm not creating an assignment. Ding dong. Bless you. All right, so now we're going to do some notes. We're going to do some chemical reacting. Those of you at home, once they break to the labs, I have to go back and watch them. So I will post a video of the reaction for you to observe, and we'll talk about it Monday. But that's coming attractions. There we go. All right, so we're going to take some notes, and we are taking notes here. Excuse you. Okay. Fire is a chemical reaction, unsurprisingly, I hope. And we are going to have some fire today, which is why it smells like burning stuff in here, but just really briefly, not charcoal briquettes. All right, your book says there's 5 types of reactions. I'll just go through them really fast. They're already listed on your note page. First one is, the book calls it combination. Many books call it synthesis. And then there's decomposition, single replacement, double replacement. I learned them as single displacement and double displacement. The alliteration works better on the double displacement. But anyway, so I will use those interchangeably, just FYI. Combustion. And then the 6th one that I add in is actually really just a type of double replacement, and that's neutralization. And I'll explain how it's different as we go. So this very first reaction, synthesis or combination, is when you have 2 or more reactants making a single product. So more than one thing on the left, which isn't exclusionary, but the ticket to determining, when you look at a chemical equation, determining its synthesis is to see one single compound on the right as the product. And this is burning of magnesium ribbon, and we're going to do that next week. So you'll get a piece of magnesium, and you'll hold it in the tongs and put it in the burners, and it is crazy. Be really fun. All right. Questions on that? Beautiful. The opposite of synthesis or combination is decomposition. This time we have a single reactant making multiple products. And that, the names kind of make sense actually for these. Decomposition, falling apart. Not surprising. Sorry, I forgot to take a roll, huh? All right. And this is a picture from your book of the ore calx, C-A-L-X, that's used to obtain pure mercury. It's a red rock heated up. Liquid silver metal comes out in oxygen gas, which of course you can't really see, but it's there. Okay, the next type of reaction is called single replacement. A single element replaces another similar element in a compound. So how do you know on these? Well, on the left-hand side, there's an element by itself. Maybe it's a metal, maybe it's not. And there's a compound, and lots of the compounds that we are going to use, most of them are ionic. So there's a metal with a non-metal or a metal with a polyatomic ion. Remember, metals form cations, non-metals, and most of the polys are anions. So here's the deal. Sometimes, I'll make it a different color. Sometimes this elemental metal can knock the other metal off the compound and form a new compound and leave the first metal out in the cold, right? So it's a single element and a compound, different single element, different compound. And in this case, it's potassium and water making potassium hydroxide and hydrogen gas. Now, it doesn't happen not everything reacts with everything, okay? And so there's something called reactivity series, which is what's on your note sheet, that helps you decide if it's likely to happen. There's no real easy way to predict it. I mean, there's a little tiny bit. We looked at, I don't know if you remember when we did our metals, non-metals lab, we looked at potassium and sodium, calcium and magnesium, and lithium, these top 5. But surprisingly, lithium is at the top of the activity list. And when we put it in the water, it was not the most reactive. It just depends on what it's reacting to replace, I guess. So there's not really an easy way to learn these. And so you're going to have a chart to look at and decide which one can replace which one else. Now, it's activity series of metals, but hydrogen's on there, and hydrogen is not a metal except that it does what metals do and forms a cation. So that's why hydrogen's on there. It can bump some metals off of some compounds, but not many. All right. The highest on the list is the most active. The lowest on the list is least active. And you'll see down here copper, mercury, silver there at the bottom. Below them on this one, below silver, is platinum and gold. Now, you probably know copper, silver, gold. Those are the coinage metals. You can find them in what they call the native state, right? We live in California, for crying out loud. The gold rush, the 49ers, right, came because there was gold just laying around in the streets, apparently. It's not very... Well, the first 4 anyway, you'll never find unreacted. Okay, magnesium you can find mostly unreacted, but it does tarnish pretty quick. You can also look at the activity of nonmetals, and the most important nonmetals we're going to look at are the halogens. Fluorine, chlorine, bromine, iodine. Cool thing with them is the top one is the most reactive, the bottom one is the least reactive. So they're in order already on the periodic table, makes it super easy. So instead of a metal trying to bump another metal, it would be a halogen trying to bump a different halogen. Fluorine always wins. Iodine never wins. So if it's iodine out by itself, it's going to stay by itself and not do a reaction. Again, the highest on the list is the most reactive. As far as so good? Okay, for a Friday afternoon, you guys are hanging in there. Double replacement reactions. Double displacement reactions happen with ionic compounds. They usually happen in solution, but they don't have to. At least one of them is usually dissolved. So we have a metal, we have a non-metal or a polyatomic, we have a metal, and we have a non-metal. So non-metals make anions, metals make cations. So get all my colors here. Boop. So if they're in solution, these compounds come apart and dissociate. And then there's just plus and minus pieces. There's positive and negative pieces in solution. The positive, if you put the two solutions together, remember when we did the little dropper bottles? If you put them together, sometimes they'll make an insoluble new compound. That was the precipitate thing. But the positive from one can go with the negative of the other. Positive from one can go with the negative of the other, okay? It's always going to be that cation is going to be at the front. Anion is always going to be at the back. So that's why I went in first. And then the outer one is second. So same pieces, they just recombined, kind of like your Lego sets. I call this innies and outies, which is kind of silly. It has nothing to do with belly buttons. But it's from back when I learned algebra, this was a little mnemonic. You guys heard of FOIL before? first outer, when you're multiplying polynomials together, right? You do the first ones on each, then you do the outer ones on each, then you do the inner ones on each. And anyway, so that was just a little way to remember to make sure you multiply everything. So that reminded me of it, right? So put the metal from one with a non-metal of the other, metal from one with a non-metal of the other, and those are possible new compounds you can make. Neutralization is just a special kind of innies and outies where you have, instead of just a generic metal, you have a hydrogen ion. Okay, and instead of a non-metal, random non-metal, you have a hydroxide ion. Okay. So guess what? When you put hydrogen with hydroxide, you make water. Okay, and then the other two are the metal with a non-metal. These are a class of compounds called salt. Now, the easiest example of a neutralization reaction makes table salt, sodium chloride, but not every salt is table salt. Salt is a generic term. Okay, so in a neutralization reaction, you take acid and a base, making water, and some sort of salt. Okay, not every salt tastes good. Lots of them will kill you if you eat them, so don't eat them. Just saying. All right, so when pH is measured, you're measuring the concentration of hydrogen ions. And if they're captured by hydroxide ions, then it makes water, which is neutral. All right, last one. Everybody good so far? Cool. The last one is the fun one, combustion. We put together a fuel and oxygen. Obviously, again, we don't have a shaker of oxygen. It's all around us, or we shouldn't be in the room. The oxygen reacts with the fuel and makes carbon dioxide and water. All the combustion reactions we're going to talk about are the ones that involve hydrocarbons. Okay, so it's reacting carbon, hydrogen, and oxygen. Okay, so lighting your burner is a combustion reaction. Questions on any of that? All right, we're going to stop there. And I am going to present the lab to you. So make sure your lab's open. I thought I made a file for this already. Did I not already make one?
Is there a paper copy to sign?
I'm going to give you a paper copy. Huh. Okay, I guess I didn't make it. All right, I thought I did. There we go. And for those of you at home, you need to stick around until we break to the lab benches. Those of you here can sign off of the Google Meet if you like. Close your laptops. People in my second period class between solitude and BS like that. Pissing me off. I know you guys don't do that because you're little angels.
Hi.
All right. Everybody needs to writing implement. Everybody needs to look. They're in the back. So the materials list is really, really big. And that's because there's 9 different reactions that we're going to do, but we're not doing them all today. Okay, so when you get back to your lab stations, there's only going to be 4 things out, well, in your boxes. 2 bottles of hydrochloric acid. One is 6 molar, one is 1 molar. We'll talk about which one to use when. There's a bottle of marbles, well, marble chips. and a bottle of baking soda, okay, sodium hydrogen carbonate. You're also going to need your test tubes and a watch glass. So that's the giant contact lens thing. Also in your boxes are matches and splints. Okay, and we'll explain why we're using those in a minute. That's all you need for today. We talked about the types of reaction. Endothermic is you'll perceive an endothermic reaction as feeling cooler. You'll perceive an exothermic reaction as being warmer. We'll talk more about that later. Again, 6 molar means it has 6 moles per liter, which is really concentrated. It's really an irritant. 1 molar is 1 mole of HCl per liter of solution. That's about the concentration of hydrochloric acid in your stomach that your stomach generates. Okay, so that's also very irritating. If you've ever had burped up stuff from your stomach, you know, it still hurts. Okay, so you're going to wear your goggles today. We're going to test for the presence of gases in this lab. There's 3 of them. Today, it's only 1 gas, but I'm going to talk about all 3 of them. So oxygen, you know, is required for combustion and for lots of things, but oxygen will make a fire brighter. Carbon dioxide is going to actually put out a fire, right? That's what's in fire extinguishers. Most common fire extinguishers have CO2. And that's because carbon dioxide is denser than air and it displaces the oxygen around the fuel and puts out the fire. Hydrogen gas is explosive. We're going to just use a little tiny bit, okay? And it will go boom, except it won't go boom. It'll sound kind of pitiful actually in here. But for oxygen gas, we're going to test it when I tell you, not today. You're going to use what's called a glowing splint. And if you get really lucky, that glowing splint will relight, but it might only glow brighter. Okay, it just depends on how much oxygen you have present. Okay, it just depends. We'll talk more about that next week. Carbon dioxide, we're going to use a lit splint. And again, since it's used in fire extinguishers, you can probably figure out it will put the flame out. Fancy word for put the flame out is extinguish. And then finally, for the hydrogen, when we get to that point and want to test for hydrogen, we're going to use a lit splint again. And this time, it goes boom, like the Hindenburg. No, it just goes whoop. It makes a cute little noise in your test tubes, but big enough volume, it will go boom. Okay, so what do I mean by lit splint? Well, hopefully it's pretty obvious. Your splints probably in the boxes by now have all been used, so there'll be a burnt end. Just use the re-burnt end. Reuse the burnt end. I can talk. It's Friday afternoon. It's fire. So that is a lit splint. No surprise. Matches are hot. Don't put them on your paper, but you can put them on the lab table. When I say use a glowing splint, this is a glowing splint. It was lit, and now it's just embers. Okay, and notice if I move faster, it glows brighter. That's because I'm hitting it with more oxygen molecules. So the lit splints can be, reused. Keep one of them clean because you're going to use that as a little shovel for reaction too. That's still adequate to test with. If it gets much shorter than that, you probably should just put it in the trash. And that's what you're going to do with the short splints and all the matches at the end. Put them in the trash in the back. Just let them cool on the lab's counters. They'll be fine. Okay, so in one of these is little rocks. So you guys remember calcium carbonate was in chalk. Well, metamorphosed chalk is marble. And so you take those little seashells and little exoskeletons and squish them and heat them up in the Earth's crust, and you make marble. So these are marble chips or boiling chips. It's to keep stuff from spattering. There should be some of these on the counter already by your station. We're going to add to the calcium carbonate, we're going to add some hydrochloric acid, HCl. And the acid that you're going to add is the 6 molar. You don't put that in the equation, but I'm telling you. And so it's right here in step number 2. You're going to use some more concentrated acid. And geologists use this in the field all the time to distinguish between quartz and calcium carbonate or marble. It says 5 drops. Just go ahead and switch it to 10. We're going to be wild and crazy. And once you've got the marbles in the test tube, put the acid on it, cover it with the watch glass, and let it sit there for about half a minute. Feel the bottom and see if you can tell a temperature change. You probably can't, but just feel it. And then one of the partners lights the splint. And when you're ready, put the splint inside the mouth of the test tube. You don't drop it into the liquid. If it drops, it's not a big deal, but you don't need to. Just put it into the test tube and see what happens to the splint. So we're using a lit splint. Circle it if you have paper. And remember to make observations before, during, and after. So before, you're going to have white rocks. You're going to have a clear liquid, clear acid, clear colorless HCl. Okay. While it's going, it's going to make bubbles. Why is it making bubbles? It's making carbon dioxide. The carbonate and the acid react. And so some bubbles come off. And what you're going to be left with in the test tube, which you can't really see, but I'm telling you, is calcium chloride. So that calcium goes with the chlorine, right? That's the outies thing. Okay, calcium with chloride. Remember, calcium is a +2, so I need 2 chlorides to make that compound neutral. And they're actually going to stay dissolved in water. They're going to stay aqueous, but you are there, okay? You look at the carbonate, there's an oxygen that's not used in carbon dioxide. That's going to go with the hydrogen. So this is a type of double displacement with the extra bonus of a generated gas. So we're going to make water as well in this reaction. And that water, of course, is going to be a liquid because it's at room temperature. Okay. Now, this is not balanced. We'll talk about that on Monday. I just want to get this part on here. So, again, once you put the acid with the rocks, you're going to see bubbles. Okay, bubbling. I'm just telling you ahead of time. Write down anything else you see, and then tell me what happens to the splint on this line and circle endothermic, exothermic, or can't tell. All right, same process for reaction 2, except we're going to use the 1 molar hydrochloric acid, so the less concentrated, the stomach acid concentration, and we're using baking soda. So sodium hydrogen carbonate is the fancy name for baking soda. Same sort of thing is going to happen. The baking soda is going to react with the hydrochloric acid. And the acid's going to make carbon dioxide bubbles, and it's going to make water. And in that water is going to be sodium, the front of the sodium hydrogen carbonate, the sodium bicarbonate, and chlorine. We're going to make salt water. Stable salt water, I guess I should say. Again, you're going to have CO2 bubbles, and you're going to test with a lit splint. And you should probably expect the same thing to happen as happened in number 1. But for the rocks, what I want you to do is, it says dump contents into sink, but that's not really true. I want you to fill the test tube with water and then catch the rocks. No rocks in the drain, okay? That's really bad for the drain, in case you didn't know. and then leave the rocks on the counter for the next period. The other one can just get rinsed out completely, rinse everything out. Again, matches in the trash. And yeah, we have just enough time to do this. I know you can do it. So goggles on. Did anybody not wear closed-toed shoes? Good. Wear an apron if you're in shorts, please. For this one, it's not too dangerous. Yes, you can get a hair tie if you like. All right. And then those of you at home, I will put up a video. They're all going back to do the reactions, and I have to go be there with them. I can't leave them alone yet. So have a great weekend. I apologize that I can't, I don't have this made yet, but I will make one up for you, okay? See you Monday. Thank you, sorry. Bye, Lena. Thank you. Bye, Joshua. You too. Have a nice weekend.